Hey, who's all here? It is time for Office Hours Part 2. It is Office Hours. If you're in the chat, feel free to say hi. Let's get the top chat on. Mubot is awake. Get the top chat off, rather. And we can do some 201, some 320, some 474, some 475. Well, I don't teach 474 right now, but let me know. We got people with the group me's going right here. Groups communicating. Let's see, no idea in Berkeley Workshop, apparently. Oh, cool. Oh, interesting. What is this? Wow, what is this? Interesting. Volunteer. Is this an event at UT? Whoa. That's interesting. I'll have to look into that. Do I know? Cool. Well, I'll look into that. If you're in the chat, feel free to say hi. Interesting. Interesting. Let's see what chat has to say. Is anyone there in chat? Chat, where are you at? It is later in the day here on a Thursday. Busy day. Got 3:20 left in the afternoon. So, who all is here? Interesting. Fourth. That's an interesting group and everything. Is it live on campus? That'd be interesting. Huh. Well. Find out. Cool stuff. Well, we're getting work done. Interesting emails I'm getting. Look at that again. Take a look right here. Where's it at? Interesting. Well, if you're in the chat, feel free to say hi. I'm reading up on stuff right here. Like Brian's just saying all this interesting. No one's here. I am streaming, right? Ah, what questions are there? We'll put the taking questions up. Replying to emails and seeing what's going on. Big day coming up this weekend. Let's see. That's interesting. Got the numbers. chat. We're fixing questions, fixing problems. If you're in the chat, feel free to say hi. Fixing problems as we're working away right here. Is anybody there? Is anybody out there? Gonna fix problems. Get some work done. If you're in the chat, ask a question. We got the chat is open with questions right now. Fixing questions as we speak. And found it. Good deal. Got that fixed. Great. Submitted, right? Submitted. Right here. Great job. Got it fixed. There we go. Got that fixed. One down. Problem fixed. Let's see if anyone's in the chat. Hey, what's up, Priya? Priya, if you have questions, let me know. I'm responding to emails right now as we do this. Going through getting emails responded. So usually I'm doing this like later at night, usually going through and getting everything going. Okay, I need to fix this now though, because this student needs something fixed now. If you have questions, let me know. Priya, so good to see you here. Can you go over number 4 with comp rules? Yeah, proportions. Let's do that. Is it the quiz or is it the... If it's the quiz, let me know which one it is because the quiz changes every time people take it. So if you're doing the quiz question, which we can do, let me know which quiz question it is because that changes for everybody. As you work through it, everyone has different quiz questions. So tell me which quiz question it is. And then I will do that. And I'm getting this fixed up here, and we'll do that next. Next on the list, we're doing the quiz question. Which one is your number 4? Nope, wrong thing right here. So I'm changing something for a student. Saw an email that was a little bit more of a kind of need to change now type thing. Good thing I saw it. Every time I go, it says, like, you have changes. You have made changes to this quiz. These changes are not saved. Well, why do you think I made them? Several factors are influenced. Yeah, several factors. Let's look at the several factors one right here. 1 second. We'll do that. Thank you so much, Priya. Let's see right here. 2 moments. I'm going to fix this. Okay, gotta find. Oh, I bet it didn't save. Canvas is so weird sometimes. There we go. And I bet there was an issue where it didn't save. Okay, let me save. You hit save on Canvas. Sometimes it doesn't save. Okay, save that. Save this. Good to go. Sorry about that. Okay, let's look at the several factors. Going to leave my email here and get the quiz going here with several factors. Warning, no access. Oh my gosh, it's a... Oh, good thing I didn't... That was Eminem playing in the background. That was the Dido song. How did that even go? Oh, that Thunderstorm doesn't... That song came out... Put the music video out quite a while ago. Yeah, we can't... We play that on stream. We will get hit with a copyright claim hard. 530 million views. Copyright claim for sure on that. So let's go check this out. Priya, we got it loading up. Somehow I had some Eminem playing. Man, that song came out a long time ago. Long time ago. In a galaxy far, far away. Okay. You know what I already have? Several factors, right? Several factors. Okay. 2 seconds. We're getting it ready right here. How's your day going, Priya? We got a lot of good work right here. We got the several factors question ready to go. We only got one question, so if you're here, drop those questions in the chat. Here we go. Several factors. 11 minutes in. Stat 200. It's only 11 minutes? Wow, it hasn't been long. Several factors. Let's go check this out. Here we go. Okay, for this question right here, it's a really good theory question. So what we need to do is we need to write down our formula. It's talking about several factors can influence the confidence intervals. Yeah, my day's going pretty good. I had a hair appointment yesterday, eye appointment today, doing some work. Pretty good day. So I'm going to write down the confidence interval formula. P hat plus or minus Z star P hat times Q hat over N square root. So with this right here, you'll notice it says for a given sample size, we can almost ignore that. It's like sample size doesn't matter.
It doesn't matter.
Higher confidence means a smaller margin of error. So higher confidence would mean a smaller margin of error. Higher confidence means a smaller margin of error. So for a given sample size, higher confidence means a smaller margin of error. So what is going to control confidence here? So what impacts confidence? What impacts confidence? What in this interval would impact confidence? What impact confidence here? So we've got an interval written. Yeah. Substitute values for each variable, and then yeah, exactly. That's what we're about to do here, Troy. And so this is a good practice. Barrett was here earlier this morning. He was like, "Okay, it's made a lot more sense." And Troy, if you have more questions, let me know. We got open questions after this, so it's Z, and so great work, Priya, right there. Z is the only thing that impacts level of confidence. We sometimes put a star on it, meaning that is going to control how confident we are. So if we increase confidence, higher confidence means the Z will go up, which everything here is the margin of error. But higher confidence means the Z will go up. So if Z goes up, what happens to margin of error? If Z goes up, margin of error will do what? Because we're going to go from like a 68 to a 95 to a 99.7, Z-score 1, 2, 3, very close to respectively. If Z increases, the margin of error will do what? Because it's going to get bigger. Yeah, pretty much doing it theoretically. Like if you understand the theory, you can do it pretty quickly, but then also substituting in values. And I think Troy's saying like they increased it and they saw like if you put in like 1 here or 2, that's exactly right. So as Z goes up, confidence would get higher. And so it's a good way. Troy, thank you so much. Good way. Let's put in some values and see it, that's going to be a bigger number right there, right? So this is going to make it go up. So it means smaller. Ooh, that's false. No. If that goes up, the margin of error goes up because you're more confident. Also, you can think about it visually speaking. We might have some of the visuals open for this. Not currently. That's just a Google form. Oh, no, we don't have another one. 4 seconds. Boop, 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 boop. Okay, so let's go to David M. Lane. Oh, I should have Mubot tell us. What am I doing, Mubot? I'm sorry, my man. David M. Lane from Mubot right there. And we're going to go here. And if we change this from a 90 or 68 is 1. It always helps to see things. 68, 95, and 99.7. 68, 95, and 99.7. As you go further and further and out, you're making more confident, wider intervals. So more confident, wider interval. And so it's not smaller. That's a counterfactual. Not true. And so now, for a specific confidence level, larger samples provide smaller error. What are we changing now if we say larger sample, Priya? What are we changing now? What are we changing now? So now we'd be changing the what here. If we say for a larger, exactly, we'd be changing N. So we'd be changing N right here, and N is the sample size. So I think Troy had a great way of doing it right here. Let's plug in some numbers. Mathematically, if you go from 2 to 200, what happens to this component of it? Going from 2 to 200, what would happen to that component here? Going from 2 to 200, what would happen to it? Like if you go from 2 to 200, we'll erase all this so we can just focus on what we're talking about. If you go from 2 to 200 to 2000, it's going to get smaller, right? Like as you make this bigger right here, you're dividing by a number. So we can see here as this value goes up, this is the margin of error of the question. The margin of error would go down. So as sample size increases, the margin of error is inversely related. And just think about it theoretically. There's a theoretical way to think of it too, that if you get a larger sample, you would understand the population better. So you'd have a more narrow understanding of what the truth might be. So larger samples lead to smaller margins of error. That is true. Like, and it's saying all else equal, like let's not change anything. Now the next ones are where it gets really complicated because they say like a fixed. Probably the next one is the toughest one. I think I've gotten it wrong before. Not today though. Maybe we'll get it wrong now. So the next one says, for a fixed margin of error. So that means we're taking the margin of error component, which is the plus or minus portion, which is equal to z, remember we were just writing this a second ago, p hat q hat over n square root. So we have a fixed margin of error. What does fixed mean? It means it's a value that we can just say, and we're just coming up with like 5. If we're doing proportions, we should probably put it as a decimal, something like that. It's fixed. It's staying the same. Larger samples. So let's talk about if the sample size goes up. Think about this. Sample size. Hey, good to see you, Vernaker. Good to see you. If sample size goes up right here, oh, looks like they know the answer. What would happen to this equation if sample size is going up right here? Just remember from the previous question, margin of error will do what mathematically? Like if you start to increase sample size, don't worry about the remaining part of this. Margin of error is going to do what mathematically if sample size goes up? Now we're trying to keep it fixed. We'll talk more about that in a second, but doing this will do what? Previous question to margin of error. Increasing sample size will do what to margin of error? So increasing sample size will decrease it, right? So what if we use this as a counterbalance? So if we increase the sample, we could go to greater confidence level. For a fixed margin of error, larger samples provide greater confidence. Let me double think this. Larger sample. Oh wait, I have it reversed. That's why. Yep. Should have put it down on this. Didn't look right theory. And Priya, 500 points. Brian got something wrong theoretically. Priya said decrease, 500 points. Great job, Priya, right there. If the sample size goes up, margin of error decreases. To counterbalance that, we could go to what confidence level? So kind of read the question. Because we want 0.05 to stay the same, so these things are going to work against each other here, as per the previous questions. But if sample size increasing decreases the margin of error, then we could go to what to counterbalance to bring the margin of error back to a stable same number, which is the question itself. If we have increasing the sample size would decrease the margin of error, that's what that down arrow represents. Well, so the sample size increasing would decrease ME. Let me write ME next to this. So if sample size goes up, we would decrease the ME. So what we could do is we could increase, or we're throwing arrow there. We could increase to counterbalance it the confidence level. Does that make sense? And this would increase the ME. So if you increase sample size, margin of error does what? This question is more complicated than we usually put on the test. Here's what we want you to really know. If you increase sample size, margin of error does what? If you increase sample size, and it's what you said just a moment ago, if you increase sample size, margin of error does what? Increasing sample size means margin of error will do what? And Vernaker, if you have a question, just let us know. We have open questions after this. It'll decrease it. So the way this question works is it's kind of saying, well, if this is going to cause a decrease, you could counterbalance it by increasing your confidence over there, which is increasing the z-score, and increasing the z-score would increase the margin of error. Like z-score, higher confidence directly increases margin of error. Higher sample size decreases margin of error. So if you were to increase the sample size and you wanted 0.05 to stay the same, you would have to change the z-score and go to greater confidence levels. Does that make sense? The question's more complicated than usually what the tests ask. test asks, usually we want you to know Z is related to confidence level, and increasing Z increases width of interval, and i.e. confidence level, and increasing sample size will decrease margin of error, and that's how many we sample. Let me know if I can explain further, but I do want to say this is usually, we don't usually go for a test question that kind of says, well, if you want to keep this constant, what could you do? I don't think we usually even do that in stats that much. That one's the one I don't like that much of, this one. For a given confidence level, having the margin of error requires twice the sample size. So for this one, take a look at the following. So now we're saying having the margin of error. Well, the margin of error is made up of a few components. We have Z star, which means you get to pick it, square root P hat Q hat over N. Z directly controls percent confidence. So Z is more of your confidence. Like when you change Z from 61, 68 to 95, you're going to higher and higher confidence levels. So the bigger the Z score, the more confident you are. And we would give them to you on the test, or on the homework, you'd find them via things like the David M. Lane applet if you had to make like a 92. So do take note how this screen is set up, and we'll put David M. Lane here in the chat again. For anyone who's watching this and wants to go over to the applet, you'll see it as a link in the chat from MuBot in a moment. So this right here is the Z score for a 92%, but if you go to higher confidence levels, you'd have a bigger Z score. Go to even higher ones and you have an even bigger Z score because it's just covering more of the values on the curve. So the more confident we are, the bigger the Z score. The Z score is directly controlling the margin of error because it's how confident we are. So if we want this to be half of what it is, we have to look at how that impacts sample size. So you would think you could just times this by 1/2, but that hasn't directly told us what N should be. We want this to go inside of the radical. Well, to do that, we have to re-express the equation. By re-expressing the equation, I mean, let's rewrite these as square roots. Because Priya, what is the square root of 4? What is the square root of 4? So just think, what is the square root of 4? Great job, Priya. 100 points. Keep it up. What is the square root? It's just 2. So does it make sense? Yes or no? This is just 1/2. Like if I write this, or if I write it with the radicals, this is just 1/2. Like that's 1/2. I know it says 1/4, but it's square root 1/4. But square root 1/4 is 1/2. We could confirm with calculator over here. Go to the calculator and say 0.25 and go to square root, and it's 1/2. So that is 1/2. But now what you'll notice is when you combine this with the radical, when you bring it inside of here, you're just literally going to take the 4 and it's going to go right inside of here. Can we erase it almost looked so good. It almost worked. There we go. So now we don't need twice the sample size. We need what the sample size? Because we just multiplied. You can combine things under radicals, if same root for the radical. We don't need twice the sample size. We need what times the sample size? 4 times. So this is false. And that's got it. And that's a good theory problem. That's a good walking through. I substituted 10 for the n and solved it, made up. Oh, and then you did it. That is 20. Then it checked it. I mean, it was to see it was split. Nice job right there, Troy. Troy, those were some 500 points right there. Good. Just, seeing if it worked. Troy was like, let me see if this worked. Let me see if this gets 1/2. And so there's the theory on it, Troy. It has to be 4 times. So if you wanted a third of it, you'd actually have to do 9 times. To get a third of your, because it'd be over here, and to get 1/3, you'd have to re-express that as equal to 1/9. So to get a third, so it's exponential growth. That's why it takes sometimes a very large sample to get the right amount of understanding you want of a population, because you might have to get a very, 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 very large sample, which is sometimes very hard to do, time and money. You want to do a little Canvas content? Let's do some Canvas content. Yeah. What does everyone think of the new setup right here? It gives me more range of motion, so I don't really reach off screen anymore. And it looks like it's not, we'll have to stream in the morning to see if I'm catching or maybe it was back there. I don't know. Sometimes it gets a little sparkly. Hey, Charlie, good to see you here. Aw, Charlie. Awesome. How's your semester going, Charlie? I haven't seen you in a while. How's your semester going? I'm going to do a little Canvas content. Let's see. I slept really well last night. So those mornings when you wake up with no alarm, woke up at like 8:10 this morning, woke up no alarm, and I was like, that was good. I really think very busy, awesome. Well, very busy is good. That means you're in high demand, doing a lot of great stuff, active life, love it. But then you gotta take some time and relax. I've been trying to use alarms as low as possible because I've really found, like, I don't know, sometimes you use alarms and why does everything say it's got updates? Sigh. Could you go over the nutrition lab? Yeah, I'll put nutrition lab on here. So we got Canvas content number 8. Nutrition lab. I think that's the hot dog one, right? I think it's nutrition lab, chapter 14, right? Chapter 14, confidence intervals. Chapter 14, confidence intervals. And there we go right there. Well, let's head over here and do a little Canvas content. Time to do it. Okay, Canvas content here at the 2640 mark. Stat tool 1. Let's do a preview it and see what we got. We'll do a version of this and see what we get. Okay, so we're doing all the confidence interval stuff. This is due Monday, so pretty big stuff. Which of the following would you not use to check the nearly normal? Great question. What kind of data are we doing when we use nearly normal? So when you're doing the nearly normal condition, what kind of data? I need people's help with this. This is the only way I can solve Canvas content is I need your help. If you're doing the nearly normal condition, which is the third condition, what kind of data are you working with? What kind of data are you working with? What kind of data are you working with? I'll show you the slide we made yesterday. We marked on the slide a few things yesterday. What kind of data are you working with when you do the nearly normal? So remember condition 1, random. And Priya's already got it. It's quantitative because the third condition is decided by the type of the data. So when we do quantitative data, we could visualize it using a what? What is one way to visualize it? What is one way to visualize quantitative data? So look up there. I'm not blocking any answers right now, but what is one way to visualize quantitative data? One way to visualize quantitative data, which, look at the first way, histogram. So we know this is a right answer now. So that's a right answer. And now we're like, how do we read this? This is a plot that tells us the probability of something being normal. That is a plot that tells us the probability of something being normal. And that's it right there, a plot that tells us the probability of something being normal. So once again, that's a plot that tells us the probability of something being normal, known as a normal probability plot. Read it, plot that tells you the probability it's normal. And there's another way called the goodness of fit test, and that sees if the normal curve's a good fit on the distribution. It's over here in the output. This one passes because the p-value is above 0.05. And what it does is it fits the normal curve on top of the data, and it says, yes, this is a good fit if the p-value is above 0.05. So is it A, B, C, or D is the answer we would not pick. It says, which of these would we not use? A, B, C, or D? Priya, great work right here. Which of these would we not use? And I do want to point out, notice how we in class, because I promise you this, I know what the test looks like. Notice how it gave you 4 things, and look what's on the screen right here. Make a histogram. Histogram, normal probability plot, goodness of fit test, and C was not one of those. Bar chart, because bar charts are for categorical data, and we're not dealing with categorical. So great job right there, Priya, another 100 points. Bar charts would not be used to analyze this because bar charts are categorical data, so we can't do that. Which of the following is not a requirement for testing means? Oh my gosh, if you get these questions on the test, you should be like, yes, this is awesome. Priya, A, B, C, or D. Medical researcher, yeah. Heart rates, yeah. Let me get that on here. You bet, Cassandra. Medical researcher, heart rates. So medical researcher. Priya, you are right because success failure is for what kind of data? Just put one letter in the chat. You'll be repeating yourself. But when you hear random, 10%, then we pause and we ask what kind of data are we working with? And if it was success failure, Priya has put a C because that is for categorical data. Priya, you're acing this. I haven't even said any answers yet. You're getting it all. Ooh, okay, wait. What is the margin of error of this interval? Now, a lot of people, when it comes to margin of error, say, oh my gosh, wait, what's the equation? Okay, I need p hat, q hat, I need n, I need square root, I need all this good stuff. Slow down. Let's think about how we find the margin of error. Let's go get some Taco Bell. The Taco Bell meal is going to cost between $10 to $14. We're getting a big meal right here. Well, maybe it's both of us getting a meal. What is the margin of error on that interval I just put in the chat, Priya? Look in the chat and tell me the margin of error. Now, be careful. There's a common mistake people make when not finding the margin of error. Well, you might have the answer for... Oh, I think you solved our question on the screen, Priya. Priya, another 100 points. Priya's already solved the one on the screen. Now, Priya, be careful. I think you solved the one on the screen correctly, but the one I put in chat, 10 to 14, because I always know like a simple example. So what's the margin of error for an interval going from 10 to 14, Priya? I think you solved the one on, and there you go. Great work. A very common mistake I see is to not divide the interval by 2. So the margin of error is always what the length of the interval. And these are things to just repeat to yourself. The margin of error is always what the length, and you can see it visually right here. So it's going to be upper minus lower. That's the length of the interval. There it is. It's always half the length of the interval. So Priya, great work right there. I think you solved the other one. And then sometimes we just forget to divide by 2. That's the most common error I see when looking for margin of error. 74 minus 64.8. That's how far they are apart. Priya divided by 2. Priya, excellent work. You're acing this. The only way to change the margin of error is to change the sample size. Priya, what else could we change about a confidence interval? We could change the what of it. He'll write a confidence interval. We were covering this just a second ago, but it says the only way to change the correct the confidence level, the z-score. Great answers, Priya. How are you feeling more comfortable with these? Because if you notice, we were covering this just a moment ago by saying the sample size here, increasing it will decrease the margin of error, and the z-score controls the percent confidence. So this would be a false statement right here. The only way to change the margin of error is change the sample size. No, we could change the confidence level. Last but not least, right back to the quiz we were just doing, decreasing the sample size will make the margin of error smaller. I'm not going to answer it, but Priya, look at the equation right here. It says decreasing, oops, here it is. Oh, you're welcome. So it says decreasing this will make the margin of error smaller. True or false, Priya? Decreasing sample size will make margin of error smaller. Decreasing sample size. So think where it's at mathematically. True or false? Decreasing sample size will make margin of error smaller. You can plug in numbers like Troy was doing. It's a good way to like check. So Priya, this is 1,000 points. Priya, if you were taking this, you would have gotten a 100 on this version right here. And if this was the test, you would have just aced every question. No, it'll make it bigger. Great job, Priya. Well-earned points. You answered pretty much most of those questions. I was just kind of helping along the way, but that's some really great work right there and really great practice in understanding the material. So great job. But yeah, 7 minutes. We reviewed the concepts. And if you notice, I want to point this out. Think about all these things we've been saying in class. I really try to make as much as I do related to what you're going to be seeing, like how we should know what the third condition is and how could you pick it. Well, random and 10%. Like if you see this, does it make sense, Priya? And great job there. When you say which of these is not required for testing means, sure, that's fine. So is 14 testing? Oh yeah, we can say it's testing. Confidence rules for means. The only thing you'd be looking at right here are these two. Random and 10% are the ones we just always give like this really quickly. So the only two you would need to consider are those. By coming to class and just practicing the two conditions we always say, if you get to this question and you don't know the answer, it's a 50-50 guess. So exactly, then we pause and we say, what kind of data are we working with? And it's means, so it's quantitative. So it's nearly normal. Well, no, wait. Is not required. Ooh, that's a weird question. You see, I almost got it wrong there. It says which of these is not required, and success failure is not required because that's for categorical. We did answer it correctly when we were doing it, but if we were testing means or doing confidence intervals for means, then it would be nearly normal because that's for quantitative. So that's what's not required is success failure. Not questions are weird. Let's do some of those questions, Cassandra. Here we go. If you want, Priya, we can do another version of that in a little bit. I've got a meeting at like 4:45, 5:45 your time. You say, Brian, you missed your meeting. I say, I never do that. Ha 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 ha. Whew. Busy day. Oh, definitely. Yeah, we'll try another version of it. Let's see. Where is the quiz? Loading up the quiz. Okay. Pause in the chat. Nutrition laboratory. Let's do a nutrition laboratory. Here we go. Nutrition laboratory time right here. Now with this one, even if you haven't been practicing, you know what we're going to do first. What is the very first thing we do? This is a really good practice question. Oh, we're making some cool graphics. Oh, I just moved my contact. What is the very first thing we do for all of these? The very first thing we do for any question is what? Priya already right there. Notation, you got it. Great job. We just want to drill ourselves to say we're going to always solve for that notation first, because the notation is going to kind of lead the question. Now, this is a chapter 14 question, so we're dealing with the mean. A lot of times the best way to find notation is just look for any number you see and highlight it. Some questions do have additional numbers that we won't use, so watch out. Now, this question right here gives a lot of great info. We'll do that. So there's going to be a trick, and I'll stop off where the trick is at for this question. Not a trick, but things you must know. It says 60 hot dogs are being tested. That's the sample size. It says the mean for the sample is equal to that. That's Y bar. The standard deviation for the sample is that. So sample standard deviation is S. This is not the truth for a population. It's the truth for us, or what we found from the sample. There's no truth for the sample. Well, I guess the sample is its own thing. But now 95% confidence is usually where the problem is. What are we using right here? We are using the following formula. And what are we missing? So if you're in the chat right now, tell me, what are we missing? We're missing a certain value, and you can just call it one thing. So we're missing a certain value right now. What value are we missing to solve the problem? If you look at what I've marked, we're missing T. So we should go over, and Priya, if you can get this, you know how to solve these problems. We've already marked the sample size, the sample mean, the sample standard deviation, and we want to understand what's the true sodium content. So I'm going to take a pause and see if you can tell me what the right T is. I'll give you a hint. We should also find out the degrees of freedom, and the degrees of freedom are equal to n minus 1. So that's equal to 59 right there. So it's 59 degrees of freedom. Degrees of freedom are, they tell us what T we are using. So in case this is your first time watching, we'll see. We're going to throw out some more points here if you'll get it right. Priya, great work. This is the T applet I like to use. It shows us the T distribution. The T distribution is basically the normal, but the T has been smashed down by Mr. T until he gives it freedom to be normal. So we have to ask, Priya, 100 points again. Priya's found it because, remember, our sample size was 60, so we need to do 60 minus 1 for the degrees of freedom, and this will control the shape of it. And I like to use this button right here and then plot the middle 95. Notice how it, very close, Mitzi. So Mitzi, good answers. This one's actually not the David M. Lane. The David M. Lane only does the what curve for us, which this is basically, but not quite. So good answers, Mitzi in the chat, worth 100 points. But remember, the David M. Lane only does the what curve. What curve does the David M. Lane curve do? It only shows us this curve. It only shows us the normal. So we need to go over here and use the T curve. Notice how this is the T distribution, named after William Gossett, who worked at Guinness Beer, teaching to the test moments. So William Gossett worked at Guinness Beer. He made the T distribution because Ronald Fisher wouldn't publish his work. Darn you, Ronald Fisher. He's not around anymore. It's like 1890 and stuff. So this right here is the correct T value for us to use, which is basically 2. We could probably just plug in 2 and get the right answer. So it's 2.0001. So 2.001. And go out here. And S over square root of n. We'll just solve away right here. There we go. And let's take a look. There we go. 36 divided by. And what have I found now, Priya? 9.3 is what? This is always how I write them. What have I found right now, Priya? I found what right here? This 9.3 especially. I'm kind of highlighting to show, as we've gone through and solved it, that 9.3 is probably the most important part there. The margin of error. Great job, Priya. Great work. Great practice. It solves the same way. It's going to be 323 plus or minus 9.3. So we're going to go ahead and use the 9.3 as the margin of error around this. So that's like our uncertainty in the estimate, because it's about 323, but I could be off by about 9.3. So as high as that and 323 minus 9.3 could be as low as this. What assumptions have you made? We assume that the hot dog weights, okay, good, right here. They use independent, which basically means random. Let me do it here. Or random, I'm not biased, and normal. Ooh, I've gotten this one wrong before. I think that's the one we're doing. Nearly normal. That's the nearly normal right there. So that's condition 1, random. Condition 2, less than 10% of hot dogs, which would assume. And then condition 3, nearly normal. Like, I've always had qualms between these two. No, don't do like some not multimodal. Is randomization satisfied? We don't know. It doesn't say, but we don't know. Is 10%? Yeah, these are less than 10% of all hot dogs. Less than 10%. Is the nearly normal satisfied? And so this right here relates to the large enough n way we just talked about if you watched the quiz a moment ago. We talked about the 3 ways by looking at the histogram and were we over here? Here we are. Here's the 3 ways. Look at the histogram, make a normal probability plot, or goodness of fit. But if you can't actually see it, you could just go in and use the large enough n basically. So this is basically doing the large enough n. So even if it's extremely skewed, if our sample size is about 40 or 50, we can do this methodology. And that's what it's pointing to in its answer that even though you don't have a histogram, you don't have a normal probability plot, you don't have a goodness of fit test, which are all these things currently on the screen here. How do you figure out part 2? Let me say it again, Priya. Which part? Which question were you wondering about, Priya? A, B, or one of these? Expand upon it. I'll pause right here. Which one are you wondering about right here? Part B. So when it says what assumptions, I don't like the way they phrase this. The answer should be randomly selected hot dogs, less than 10% of the population, and the population of the hot dogs are nearly normal. I don't like that answer right there. I'm 99% sure I'm right. That's the only one I'm worried about on my not today, my Pearson streak of right answers. That's the only one I'm worried about right there. And it does say to 1 decimal, so make sure to round to 1 decimal there. So this right here, and then the randomization, we don't know. It doesn't say. So it says like, yes, there's definitely evidence. It doesn't say. It doesn't say anything about random. It just says hot dogs were selected. Yes, 10% of this means it's less than 10% of all hot dogs. If you work for a hot dog factory and you take 60, it should say, yes, I am pretty certain that 60 is less than 10% of all hot dogs. So I'm pretty certain on that. Is the nearly normal? We don't know, but since the sample size is large, we're probably good enough. We don't know the shape of the distribution, so we can't really say. We don't know, but we're probably good enough. Probably kind of an odd question in some ways. I got to make sure. No, I'm not going to get something wrong by not selecting. And then what does our interval mean? Use your interpretation. I am 95% confident that the true mean content of sodium for these hot dogs is contained in the interval blank to blank. So what does my interpretation sound like, Priya? A, B, C, or D? When I say I am 95% confident that the true mean sodium content for these hot dogs is contained in the interval 310 to 330. I'm just saying kind of the interval. I am 95% confident that the true mean sodium content of these hot dogs is contained in the interval 310 to 330. Does that sound like A, B, C, or D from those answers written? D might be a little close. Let's see what's wrong with D. 95% of the sodium content in this type of hot dog will be contained in the interval. So we're trying to figure out the true. So we are 95% confident the interval contains the true mean sodium content. And they just don't say the interval is the only thing they're not doing right here. They could say we are 90% confident the interval blank to blank contains the true mean sodium content. So kind of look for your components. I wish they stated the interval. The reason they don't state the interval is because that would give away the answer to the question. So if you think theoretically, why are they not saying the interval in their interpretation? It's because then you'd have the answer to the question. So then they couldn't say, what's the interval? If we were to put the interval in, it would say, we are 95% confident the interval 310 to 330 contains the true mean sodium content of hot dogs. Now watch me get one wrong. We didn't. Oh my gosh. Mark's over here. But no, it's a good question. Any questions on this one, Priya, before we do the next one on the medical researcher? Anything you're wondering about on how it works or how we got this? Remember, I am 95% confident that the true blank is contained in the interval blank to blank. And there are variations on it, but a student one time said, do I have to say it that way? And I'm like, well, I mean, you can change it, but then the more you change it, the more I'm like, Like if you said this and you put the numbers, that'd be fine. Like, we are 95% confident the interval 310 to 320, 330 contains the true mean sodium content of these hot dogs. Not yet. Which thing not yet were you wondering about? Which thing you're wondering about? Let me know. And so, Priya, thank you so much. Just keep asking questions, whatever you're thinking. I'll hang here for a moment on this screen, but just let me know what you're thinking or what you're wondering about. Play a little chill music. Got one more class today. My parents are going to be in town. Well, they are in town. Probably in town right now. They might be at the hotel across the street. We got a class. We have one more class today. Got a meeting here in 25 minutes. Oh, you're good? Okay, good. Woo! Back to the main screen. Awesome. Let's do this. We'll do the medical research question. Flights. Medical researcher. Priya, if you think you don't know chapter 14, you're about to find out that you know chapter 14. So Priya, watch this. Priya, I have a feeling you will ace this question. Let's do it. Okay. I'm going to start down here on this. What is the margin of error of this interval? Remember, we just saw that on a Canvas content. So that interval there, Priya, find the margin of error of that interval, and then we'll talk about how we found it. So let's just start with the margin of error and just tell me how to find it. I think it's the easiest thing to go to right here. So how would we find the margin of error? Just think mathematically, we would take that and do what to it? We can go to our example. So there's the numbers of the lower and the upper. And we talk about, we're going to go get some Taco Bell. Taco Bell is going to be $10 to $14. I think Priya's already done it. Great job. Another 100 points. We're going to take half the length of the interval. So remember, if dinner at Taco Bell is going to be 10 to 14 bucks, we're getting the Chalupa Supreme tonight. So we're going to go from 10 to 14. We'd have to go through 2 in the middle, or 12 plus or minus 2. So half the length of the interval. To get the length of the interval, take the two numbers and find out how far they are apart. So this is just the upper number of the interval, the higher number, minus the lower number of the interval. That's the distance numbers are apart, and then half the distance. Great work right there. And round to 1 decimal. So there it is. Make sure to round to 1 decimal. If you get an error from that, we'll fix it. Now, if you remember the interpretations and do practice writing them, this one's actually excellent. So A, B, C, or D for the interpretations. Once again, I'm going to see if you can ace this because I think you got this. I saw this question. I was like, I know you can do this. We've been practicing these all day. Boom, right there. See, another 100 points. I usually say I am 95% confident that the interval blank to blank contains the true mean heart rate of the people. So it has our 4 components. We state our confidence level. Let me show that on the screen right here. Whenever you are interpreting an interval, please use the 4 components of interpreting an interval. The 4 components of interpreting an interval are stating your confidence level, also giving the parameter of interest, and the lower and the upper. And I emailed Terry, so I think we're going to hear this. We're in the 24 hour, so my interval will be true if it happens before I go to bed tonight. We will have met Brian's 95% confidence interval. I am 95% confident that the test grades will be released within the 24 through 36 hour period. Make sure this is usually where mistakes happen. People usually don't say what they're interested in. So we are 95% confident. Here's your interval, and we're interested in the true mean heart rate. Last but not least, it says the researcher had to calculate a 90% confidence interval. Would their margin of error be larger or smaller? So I'm not going to say the answer, but I want you to think how it works when you go from like 95 to 68. So if you go, 68, 95, we're going 95 towards 68. So what do you think? Larger, smaller, the same? They made a 95, And now they're going to say, well, what if we made it 90%? So, and this is exactly what we've been talking about, like with almost all the questions today. Boom, Priya, you did it. You just got another 100 right there. So if you notice, this is why we really have been practicing a lot of these concepts, because knowing how to do confidence intervals for the proportion, it's the same thing. Frankly, this whole question really didn't have any sort of calculations for the mean. Everything in here has been just things we could do knowing how to do a confidence interval for the proportion. Does that make sense? Like the interpretation was still, I am blank % confident that the true blank is contained in the interval blank to blank. The margin of error is still half the length of the interval. That's how we know it as that. And then it still works that if we go from 95 to 90, it'll be a smaller interval. So great work. And that's where I want your practice to pay off, because we have other chapters that do this. Just so you can see, and hopefully I can build some confidence. And if you're thinking, okay, I'm getting this, this is making sense, let me show you something we will be doing like in 2 weeks. You say 2 weeks? No way. So this is a question 2 weeks away, if it ever loads. We're going to go here to a 2 week away question. And let's go here to preview this. And if you notice this confidence intervals, this one's a little bit tougher, but look what it says. Find the margin of error. So that's an interval, right? Trying to estimate the difference between education techniques. What do you think I should do, Priya? I've got an interval, and I want to find the margin of error of it. So this is a chapter 17 question, which will be probably start of a week and a half from now. So we haven't covered this. I haven't told you anything about that. Take half the, what? Take half the distance? No way. So go upper. Now you have to be careful. Look, notice how it's a negative. So upper minus lower is actually going to be adding it. So that's probably the trick. And there you go. Type, it says round to 3 decimals. Oh my gosh, Priya, 500 points. There you go. Margin of error is half the length of the interval. Done. Solved. You've already got, if you did that right there, you've already got, well, look, wait. If a 95% confidence interval was created, so now we're going 95. We're at a 90. So if we created a 95, the margin of error would be what? So if we create a 95 instead, no, if we create a 95, yes, it'd be larger, because the critical value would what? Which is the T or the Z. Remember with CV critical value? Because this is a T for this one. Would that be larger or smaller? So the margin of error would be larger because and this is what we're talking about with the Z, it would increase, exactly. And the margin of error, and this literally confirms, it's just reiterating, because the margin of error increases as the critical value increases. It's like the most redundant. The margin of error would be larger because the critical value increases as the confidence level increases, and the margin of error increases as the critical value is redundant. And then last but not least, explain what this interval means. So with 90%, this one's tough. Or maybe there's more. I think there's a few more parts to this. Maybe we should stop this question. This one right here. Since the interval is negative on this side, with 90% confidence, students in non-traditional math, so that's the traditional. Students, we have to do students because it's the mean. So it's either A or D because it's for students, not a student. Students in the traditional math will score on average between, okay, so traditional is that one. Yeah, no, wait, no, it's this one. This much, that much lower, because this is the traditional. Students, no, wait. Oh my gosh. This means the traditional is higher. I think this is right. My brain's breaking today. I think it's 8. Wait, did you get it right, Priya? Oh my gosh. Let me double check as we do this. With 90% confidence, students in the non-traditional math will score on average between 3.234 lower. So this is the non-traditional. It might mean that this means this much lower, or that means that much higher. That is right there. Wow, Priya, great work. Woo, you got it right. Does this report support that there is a difference? No, because 0 is in the interval. The interval contains 0. Therefore, yeah, we think there's no difference. And that right there was 30% of that homework. We just did 30% of the homework. The bite question is a fun one. That one you actually have to work the mathematics on. We're trying to estimate the difference between these two groups, and the difference could be 0. that means there might be no difference between them. So anytime you're estimating the difference between two groups, if you think the difference could be 0, it's like, well, maybe this group does a little better, maybe this group does a little better. I don't know, maybe I don't know which method's better, but that's a topic we'll go into more on another day. But if you notice a lot of our concepts here, this is why when we were doing lecture, I was showing all the equations. That what we just covered right there was this chapter right here. So you notice means are important, and we were comparing the means of two groups, and we were just doing the hot dog question, which was this, and earlier we were doing proportions. So once again, our intervals we're using, and that's the critical value we were talking about. And as the critical value increases, confidence increases. So a lot of the theory stuff, margin of error is half the length of the interval. We're just going to keep practicing. And I think Priya said, let's do one more Canvas content. Might end on that. Let's go over here and check it out. Priya, amazing work. Here, we'll turn off the taking questions screen right here. Maybe I'll cut a video. Let me make a 320 video. Let's see. 320. Okay. My brain shut down for a moment. I said 320 and I thought, let's do some 320, but we are doing Canvas content again. More Canvas content. Endless Canvas content. Sounds like it's a song like, more Canvas content. Endless Canvas content. Canvas content. There we go. And we're going to go grab it over here. And Canvas content. Ooh, might save it for the other class. I don't know why it needed to be saved. That fixed something if something was broken. What is the difference between SE and margin of error? SE is a component of the margin of error. So the margin of error has two things. Margin of error has one. Here, I'll write it here in the background so you can see it as I talk about it. 2 seconds. Okay, and then I'll disappear. So the margin of error has two things. Margin of error is comprised of the z-score, or some critical value, and a standard error. So margin of error is the plus or minus on an interval, where the z-score controls percent confidence, and the standard error is like a measure of variation within a variable. If you look at an interval, a different one we're doing today, y bar, and as soon as you see the plus or minus, you know you've entered into the margin of error. Oh, no worries. This is great for people to hear. So the critical value is decided by the t here, and the standard error is s over square root of n. So this right here is the margin of error, denoted by everything after the plus or minus. And the critical value is the t used with n minus 1 degrees of freedom. And the standard error is the s over square root of n, which is a measure of variation within a variable. Standard deviation, square root of n. Very simple, similar to the central limit theorem with sigma over square root of n. But yeah, so that is some good questions. Exactly, s over square root of n is the standard error. And that's the standard error for the confidence interval for the mean, where if you do a confidence interval for the proportion, it's p hat plus or minus z. And then here we're on the main screen. This is such a good question, Priya. We'll talk about standard errors really quickly. So margin of error and standard error. So it's important to know that these formulas have a format to them where when you're looking at this, you have a margin of error is everything after the plus or minus, and the margin of error here is very clearly going to be wrong color. It's going to be everything here. Different formula. And then we have p hat q hat over n square root. And so this is the standard error. And that z-score is the critical value we use to get the percent confidence. But one last thing right here. Y bar 1 minus y bar 2. Now that's what we're estimating. So let's put it in parentheses right there. The difference between two means is what we're estimating. And then everything after the plus or minus is going to be the margin of error. This one's a little bit larger. We have a t with degrees of freedom via a complicated formula. It's too complicated, we say. We'll literally not solve for it. And then s1 squared over n1 plus s2 squared over n2. and that is the standard error. So that's a measure of shared pooled variation between the two. This is a pooled t-test, but we just call it the two-sample t-test. Rather, a two-sample t-test with pooled variance. Standard error is going to measure the variance for us, the variation in the variable. So it's just a measure of like, well, standard deviation is variation. So this is like variation of the mean. It's a good way to think of it right there. So the confidence interval has in it a confidence level. Yeah. Oh, Kristen, so good. So much great work. Yeah, I just got a haircut for the wedding. Had an eye appointment today. Gonna drop a lot of money on some glasses and contacts, and they're giving me new contacts, and I'm a little scared because they were like, "Oh, you might have some distortion around the." Like they show me this thing. Oh my god, webpage. They showed me a picture, and then we're gonna do the Canvas content real quick again. They're like, you're gonna have like this, like it was like, you will see if like there's like a house over here that'll look good. This is like your distortion will be over here on the sides because it's like it's a bifocal lens because I'm getting old. And so like my near vision will be really good, but then I'll have like distortion at like medium length. Watch it be like this screen is right at that medium length, and I'll be like, can't do it. I'll tell them I need to stream with it. Cause yeah, it looks like a baseball. So it's like what I'm hoping is the computer screen I'm looking at is like not right here, because it's pretty close to me. We just made a new setup, but yeah, it does look like a baseball, doesn't it? So it's kind of like a baseball, and they were saying how the sides will be like distorted, and I'm like giving this. Yeah. Well, I got to see my retinal nerve that goes to like my brain. It was pretty cool. Maybe they just showed me that because they thought I'd think it's pretty cool. But they showed me, and like it seriously looks like it's like this, and then it's like going off like this with like these things. Has anyone seen the new Suicide Squad? If you haven't seen the new Suicide Squad, go check it out. Won't spoil anything, but if you've seen it, you'll know why I'm saying like retinal nerves and stuff. I've had 2 eye surgeries, and my vision's really bad. And then the text said, the person like walking me through this stuff was like, yeah, your astigmatism's pretty gnarly. She was like, you've got a pretty high level. I think I'm at like 300 something, higher 300s. She was like, usually 200's kind of high. But she's like, you're 350, 360 or something. And she was like, yeah. And then it was like, I was just a little bit away from like medically necessary contacts. But so it's like, yeah, I know if I take my contacts out, it's really bad, but I can see decently. People are going to say, don't go on the road near Brian. Oh, no. Here we go. We'll put, we'll get started here on the next question, some Canvas content. So, start some Canvas content. 104.35. Okay, Canvas content number 8, part 2. Yeah, they are like, do you look at computer screens much? And I was like, I don't ever look away from computer screens. I like had my phone out, and I was like, I only look at computer screens. I put them on my camera, and I was like, yes, person. I should have done that. Like coming with like an Oculus on and be like, I walk around in VR. Don't VR drive. Don't do that. Don't do that. Okay, here we go. Let's get serious. Yeah, I look at computer screens way too much. Haha, my eyes are bad. Okay, so with this question right here, we're doing some Canvas content. Which of the followings is not a way to check? And we'll review this, but I bet people automatically know which of these is not used to check the nearly normal condition, because the nearly normal is dealing for quantitative data. D right there, bar charts, because bar charts are, say it with me, for categorical data. So that's a instant elimination, but do remember, all my Word documents, I hoard Word documents. Do remember that we did cover the condition down here after Mr. T, where we talked about, all right, have a great day, Kristen. Philanthropic. I think we have that one in the morning office hours. I'm heading off to a meeting in a little bit. Check out morning office hours. It'll be, I haven't put the timestamps in, but it'll be at the 53:43 mark, Cassidy. I'm heading off to a meeting with a student here in just a little bit, in 8 minutes. But 53 minutes into the morning office hours, you'll see me do the philanthropic question, and that's posted to the YouTube channel. So make sure to look at the videos, and you'll see morning office hours 53 minutes in, and I'll post the timestamps here a little bit on the video. If you can't find it, let me know, and I will send it your way. But have a great day, Kristen, right there. I'm going to meet with the student here in just a little bit. Which of the following is... do we have the same? We just did this one. Success, failure. Okay. The only way... It's basically the same questions. Okay, we got a little bit different at the end. The only way to change the margin of error is to change the sample size. So we've been doing a lot on that today. Is the only way to change the margin of error to change the sample size? Like, there's sample size. Is the only way to change it? Explain to me false. And why is it false? You are correct. There's more ways to change the margin of error, and this is a great thing we were just covering a second ago, last segment. It's you don't have to just change the sample size. What else could you change? The Z or the T, the critical value. Great work right there, Priya. The critical value, the Z or the T, controls confidence level. Larger T, larger Z, and T is for Mr. T intervals, the mean intervals. He's mean if you're doing drugs. He's nice elsewise. So that's very false. Decreasing the sample size will make the margin of error a smaller value. So we can see that theoretically right here, that if you decrease sample size, margin of error will get wider. So we're speaking specifically about that right there. So if that goes down, you're dividing by a smaller number. Dividing by a smaller number means the interval will get, so if you decrease sample size, the margin of error gets wider. So specifically, it's just, let me do a new sheet. So if sample size goes down, this quantity would go up, which is a component of the margin of error. So this is the standard error. Yeah. Saturday. There's a sign on the door with her dress behind it that says, "None shall pass." Not allowed to go through that door. My parents are in town. They're over at the hotel across the street, I think. So, well, thank you. Appreciate that, Kristen. So, yeah, I think we did. We did vitamin D deficiency. I think that's in yesterday's videos. We didn't do it today. We definitely did it recently. So Cassie, I can send it your way. We did vitamin D deficiency. Let me change. I think sometimes people can't find the videos because I don't order the playlist. So while we're finishing up right here, I'm going to order the playlist and get it so people see the most recent videos at the top. So I think some people are like, oh, he didn't stream office hours, and it's because I didn't move the videos to the top of the playlist. Oh, I haven't done that for a while. I wish it just auto put them at the top of the playlist. Wow. Move to top. And then I think people are like, he hasn't streamed office hours. But I do. It's organization. It's consistency, which I'm not perfect at. I'm sorry. Okay, so, and then I need to move that. That needs to be moved. Okay, so now the playlist has been fixed, and I'll drop you a link, Cassidy, here in a second. Okay, so let me find you that one. Oh, that was a slow one. Slow off, service. Vitamin D. Vitamin D deficiency. We did it. I know we did it. There it is. All right, number 4. We did it yesterday. Here you go, Cassidy. Yeah, sorry, it's my fault probably. So I tagged you there, Cassidy. Have a great weekend. Thank you so much. No class tomorrow. No class. We're just finishing up. 4 minutes till meeting. So decreasing the sample size to make the margin error smaller. False to make it bigger. A success failure condition for a confidence interval for portions requires there to be, what do you think right here? At most or at least? Which of these sounds right? So the success failure condition is NP hat greater than or equal to 10, NQ hat greater than or equal to 10. It's not about binary data, as the last test said, as a trick, at least. Exactly, because the condition can be written as, and great job, Priya. I think you can ace this, I think. And remember, these are test questions. The more you can get these with less help, which you're doing, the better you are on the test. So at least 10 successes, at least 10 failures. So good work right there. I think we got another 10 out of 10. And always be writing these down, especially if you see me doing them, just practicing them, understanding them, and then knowing them theoretically too. Notice how a lot of these questions just go to the theory we're doing, unlike confidence intervals and what it means and what the margin of error is, what the t, the critical value. So understanding what these are formulaically. But I think that's got it. We're going to head off because I'm going to meet with a student here. But I want to say great work. I guess the next time you see me, I'll be a married man. Ah! Sorry about the... Oh, no. Don't, Priya. Priya, 500 points. Don't worry. The thing is, and I try to tell everyone this all the time, get it wrong here. Get it wrong all the time here. We're here to practice because you'll get things wrong. Remember earlier today? Remember I like reversed it? I had like the down and the up arrow and I reversed it. So I got it wrong too. So, you know, it's just, you're going to get things wrong every once in a while when you speak. But it seems like you really know it. And I was really impressed because we did that question on the means and you were just like, you were doing the margin of error and everything before I was. You just had all the answers. Thank you so much. No, you're doing great. And it's just about practice and never fear about getting anything wrong here because, you know, I get things wrong. Remember, I entered a decimal wrong, and I think this morning on the My Pearson, it was like, you got a 60%. I'd be emailing Brian saying, whoops, I didn't put in the right decimals. It happens. Because like, I actually went over into R and started to like code like how to solve it. And yeah, I was like, what is going on? But we got some cool stuff. Check this out, Priya. I'm going to show this to my class. This is one of my students actually got this working. So you know how we've been doing regression? But what if you could do regression in, wait for it, it's going to load, it's going to go full screen, right? What if you could do a regression in 3D? This is a 3D regression model. 3D regression model right here, 3D. So pretty cool right here. I'm wondering, I think it's doing it a little bit differently. I think it's doing like it's interesting. We need like a polynomial model through this because I think this would actually need polynomial fits because we should have a plane rather. I'll tell him that. I'll say like, we actually need a plane for this. But he was, yeah, I know it's really cool. And this is all being done with R right here. He helped. I found the code. He went through and kind of fixed it up. And so big shout outs to my student right there, kind of having some fun with this and making some neat plots. And yeah, so I'll be showing that to the later class, but I'm going to head off, meet with the student, and I'll see everybody later. Bye for now. Bye.